Hello student, in this video lecture we are going to discuss about how to develop a flexibility matrix for the given coordinates. So as we already know, the order of the matrix is equal to number of coordinates chosen. Then so the flexibility matrix, it is always a square matrix. Okay, so in the square matrix number of rows and number of columns are same. Okay, so the element of the flexibility matrix, that is Fij, is equal to a displacement produced in the direction I due to the unit force in the direction J. So it is from the definition of flexibility matrix. So what is the definition of flexibility matrix? Displacement produced by a unit force. So that is the definition. So therefore Fij is equal to displacement produced in the direction I due to the unit force in the direction J. I represents at what location. So what location we are going to measure the displacement. J represents at due to which force produces the displacement. Okay, so we have to follow these steps. So step 1, so in order to generate the first column of the flexibility matrix, we have to apply unit force so in the first coordinate direction. So unit force, it includes both forces and moments. Okay, then measure the displacement in the all the coordinates. Okay, 1, 2 and up to n. So this is for first column of flexibility matrix. Then second column of flexibility element, again it is determined by applying unit force along the second coordinate direction and measure the displacement in first, second up to n coordinates. So let us see the example. Example question, develop the flexibility matrix for the beam coordinate as shown in figure. So let us consider cantilever beam. At the free end, they marked 3 coordinates. So one is coordinate 1 and 2, 3. So coordinate 1, it is along the axis of the beam. So coordinate 2, it is which is perpendicular to the axis of the beam. Then third, it is a moment like coordinates. Then the length AEI of the beam are constant. So solution, so we already know. So what is the order of the matrix? Which is equal to number of coordinates chosen. So in this case, how many coordinates? In this case 3 coordinates. So therefore order of the matrix is equal to 3. So therefore it is a 3 by 3 square matrix. So flexibility matrix, F is equal to F11, F12, F13, F21, F22, F23, F31, 32, F33. Then so first step 1, so develop the first column of flexibility matrix, apply unit force in the direction 1 only and measure the displacement in all the coordinate direction. So this is our beam. So apply unit force in the coordinate 1 direction only. So along 1 direction, along horizontally, we have to apply 1 kilonewton force at a free end of the cantilever beam. So because of that unit force, it elongate delta in the direction of axis of the beam. Okay, so therefore the F11, so F11 means, so displacement in the direction 1 due to unit force applied in the direction 1. Okay, so therefore F11 is equal to so displacement in direction 1 due to unit force in direction 1. So therefore F11 is equal to it is also represented as delta 11 is equal to PL by AE. So we already know axial deformation of the member, axial loaded member is equal to PL by AE. In this case P is equal to 1. So therefore 1 into L by AE. So therefore the flexibility is equal to L by AE. Then F21 means a displacement in the direction 2 due to unit force in the direction 1, which is equal to, in this case F21 is equal to 0. Why it is? Because so we applied the force, unit force, along the axis of the member. So therefore it can deform only along the axial direction. So there is no transverse displacement. So therefore F21 is equal to 0. Then F31 means a displacement in the direction 3 due to unit force in the direction 1. So in this case a third coordinate is a moment like coordinate. So therefore we have to measure the rotation in the third direction. Okay, since the in the beam subjected to only axial force, so therefore there is no rotation at the free end. So there is no transverse displacement and there is no rotation at the free end. Only the beam subject to axial deformation. So therefore F11 is equal to PL by AE. P is equal to 1. So therefore L by AE. So other two things, F21 and F31 is equal to 0. Then step 2, to develop the second column of flexibility matrix. So for this we have to apply unit force in the direction 2 only. So remove the unit force in the first direction, only we have to apply unit force in direction 2. Then measure the displacement in all the coordinates. Now let us apply unit force along coordinate 2 of this beam. So therefore the beam initially it is horizontal. So because of this transverse force it deflects like this. Okay, then measure the displacement along first coordinate direction, second coordinate direction and third coordinate direction. So this is our cantilever beam. At the free end we applied unit force 1 kilonewton force. Okay, so therefore we have to measure a displacement in 3 coordinate direction along first direction, second direction, third direction. So because of this transverse force at the free end, so there is no axial deformation. So therefore displacement along coordinate 1 is equal to 0. But displacement along coordinate 2 is equal to delta. Then displacement along coordinate 3 is equal to the rotation. So this value. So this is the moment thing. So therefore we have to measure rotation. So how to measure this delta and theta? So it is measured from any of the displacement measuring methods, deflection and slope measuring methods. So in the strength of material we already studied different method. So moment area method, conjugate beam method, double integration method. So whatever it may be. So you may use any method. So in this case I prefer to use a moment area method. So for the cantilever kind of structure, so moment area method is more convenient compared with the other method. So therefore I use moment area method. So this is our beam. So because of this point load at the free end, the bending moment diagram will be like this. So 0 at the free end, maximum moment at the fixed end, which is equal to 1 into L. So force into moment is equal to force into perpendicular distance. So 1 into L. Then M by EI diagram. Draw M by EI diagram. So EI of the beam is constant. So therefore M by EI diagram ordinate at a fixed end is equal to L by EI, at the free end 0. Now measure the rotation and displacements at the free end. So we know the change in slope between any 2 points in a beam is equal to area of M by EI diagram between A and B. The change in slope between any 2 points equal to area of M by A diagram between A and B. So we apply the change in slope between point A and point B, A and B. So therefore theta b minus theta a is equal to area of m by a diagram between a and b. So this is as per first law of moment area method. So therefore theta is equal to area of m by a diagram. So theta is equal to half. So m by a diagram is a triangular in shape. So therefore theta is equal to half into L into L by EA, which is equal to L square by EA. Then displacement at the free end delta is equal to so displacement or the vertical intercept between any two tangents is equal to a moment of area of m by EA diagram between A and B about B. So by second law. So therefore delta, the vertical intercept between point 1 and point 2, the vertical intercept between two tangents, that is so this is the deflected curve. So draw tangent at a point. So this is a horizontal line. So it is along the axis of the beam. Then another tangent at point B. So this is another tangent. So therefore the vertical intercept between any two points, which is equal to moment of area of m by a diagram between A and B about B. So for the cantilever beam, this vertical intercept is equal to deflection at the free end. So that's why I prefer this method, moment area method, for cantilever structure. So therefore, so area moment of area of m by diagram means area into perpendicular distance, that is half into L into L by EA into 2/3 of L from B. So therefore delta is equal to L cube by 3A. So these two things you may directly found from the standard formulas. We already know the cantilever beam subjected to a unit subjected to point load at the free end means deflection at the free end is equal to PL square by 2EA. Then deflection at the free end is equal to PL cube by 3A. So substitute P is equal to 1. So theta is equal to L square by 2A. Delta is equal to L cube by 3A. Now write F12. So F12 means a displacement in the direction of 1 due to unit force in the direction of 2. So in this case we applied a transverse force. So therefore axial deformation will be 0. So therefore 0. Then F22 which is equal to L cube by 3A. So F22 means a deflection or displacement in the direction of 2 due to unit force in the direction of 2. So our coordinate direction 2 is in upward direction. So in this case displacement also in upward. So it is taken as positive, which is equal to L cube by 3A. Then F32 means a displacement in the direction of 3 due to unit force in the direction of 2, which is equal to theta, but the sign is negative sign. Why? It is because theta, the beam rotates in anti-clockwise direction, but coordinate 3 as shown as a clockwise direction. So the both are opposite in sense. So therefore put minus. F32 is equal to minus L cube by 3A. The next step 3. To develop the third column of flexibility matrix, apply unit force in the direction 3 only and measure the displacement in the all coordinate direction. So in this case we have to apply the unit force, that is unit moment in the direction of 3. Why? It is because this coordinate is represented as a moment. So therefore we have to apply unit moment at the free end. Then again measure the displacement of joint B. So along coordinate direction 1, along coordinate direction 2, then along coordinate direction 3. So in this case, so moment, clockwise moment applied at the free end means the beam displaces in a clockwise direction. So therefore rotation is in clockwise, displacement is in downward direction, vertical displacement in downward direction, and there is no horizontal displacement. Then once again use a moment area method, then determine the values of theta and delta. So from the standard formula we already know, so cantilever beam is subjected to couple at the free end. Moment at the free end means a slope theta is equal to ml by ea. Delta is equal to ml square by 2ea. Put m is equal to 1. So theta is equal to L by ea. Delta is equal to L square by 2ea. or you may use a moment area method. So with the help of moment area method, you may find theta and delta. Then write F on 3. See, F on 3 means a displacement in the direction of 1 due to unit force in the direction 3. So because of the couple at the free end, so there is no displacement along the axis of the beam. Okay, so without axial force there is no axial displacement. Only axial force produces axial displacement. So it is a bending moment, it can't produce any axial deformation. So therefore F13 is equal to 0. Then F23 is equal to minus L square by 2EA. F23 means a displacement in the direction of 2 due to unit force in the direction of 3. So second coordinate will be a transverse force. So therefore we have to consider the displacement. So force means displacement, moment means rotation. So second coordinate will be unit force. Second coordinate will be point load. So therefore we have to measure the displacement. So our coordinate is shown in upward direction, but displacement is in downward direction. So therefore we have to use a minus sign for this. So therefore, so F23 is equal to minus L square by 2EA. Then F33 is equal to, so displacement in the direction of 3 due to unit force in the direction of 3. So which is equal to rotation. The third coordinate will be the moment. So corresponding displacement will be the rotation. So rotation is equal to L by EA. So direction of both third coordinate and rotation will be same. So third coordinate is a clockwise moment. So therefore rotation also in a clockwise direction. So therefore it is taken as positive. Finally the flexibility matrix is equal to this. So from the property we already know that diagonals are always positive. Other elements are it may be a positive value or negative value or a zero value. Okay, thank you.